Conditional probability. This is stuff you've actually talked about before, and every year I keep kind of going back and forth as to how much I want to get bogged down in the notation. And what I've decided to do this year is I'm just going to work through the problems with you, and then when we revisit them later this year to prepare possibly for the AP test, that's when we'll start looking at the notation a little bit more in depth and seeing kind of why it works out that way. Because a lot of these, I think if we just talk about them, they will make sense, okay, without looking at all of the notation. Okay. So conditional probability. So obviously there is some condition on this probability. That's what we're looking at. This one is kind of lengthy. It's the probability of an event occurring given that some other event has already occurred. So it's the probability of this new event coming up if I know something else has already happened. The notation is pretty important. It is the probability of, right there is the notation, B given A is how you would read that. So I'm trying to find out what's the probability of this event B happening if I already know event A has happened. It's probably, I would say, yeah, B given A there, it's just a vertical line. Yep. But make sure you make it very distinct so it doesn't look like, say, a 1 or divide by or something like that. You know? And at this time is where I could give you a much longer in-depth version of what that is, and we're going to save that for a little bit later this year when we revisit things. So this is an instance where here we would say 2 cards are selected from a standard deck at random. You're going to find out random being a very important word this year. Find the probability that the second card will be a queen given the first card is a king. I've left this very open because I think that you should be asking something first before you try and answer this. Well, I'm hoping that you know there are 52 cards in a standard deck. Yeah, what we really need to know is the card replaced? Does that make a difference in our answer if that first card is replaced? Most definitely. And I'm going to tell you here that the king is not replaced. So we'll make a note of that. So king not replaced. Again, I left that very open to see if anybody would say something. So what we're really looking for here is, if I put it in notation, we could say, what's the probability of getting a queen given that what has already happened? I've gotten a king. Now, do you notice, did I have to use the B and the A that were up there? No. Can you if you want? Sure. But I think a lot of times it's more helpful to write something that means something in the problem to you. So what's the probability of getting a queen knowing that a king has already happened, but then we have to know how did the king happen and did it get put back in? Okay. So let's face it. Well, what we would do is we would say, well, I know that there was already a king taken out. Agreed? So now, is that getting put back in? Apparently not, right? So now how many cards am I dealing with? I'm only dealing with 51. So you'd agree, if I were to write down the entire sample space, there would be 51 options in there, minus the 1 king I took out, correct? Okay. So we know in that sample space there are 51 options. Of those 51 options, how many of them are the outcome that I want? 4 of them, right? All of the queens, okay? Now for you, this is very easy. But think back a couple years ago when we had the exchange student that took stats. It had no clue what playing cards were. Okay? Well, it was a student that came here for a while that was from another country, yes. And so that made this very difficult. So we had to revisit what playing cards were for that particular student. So for you, that was quite easy, right? Okay. So that is basically the probability of getting a queen knowing that the king has already happened. Does the answer change if I put the king back in? What would be the answer if the king was replaced? 4 out of 52 or 1 out of 13, right, if you reduced it. Very good. So do you see how we have to figure out what actually happened a little bit more than what's here, but do you get the notation? Q given K is queen given that the king happened in this case. Okay. So here's something very, very huge. Independent events versus dependent events. Independent The occurrence of one event does not affect the probability of the occurrence of the other event. And here I think I will give you a little bit of some notation here in just a little bit once we also talk about dependent events. Well, based on that first definition, I think we can figure this out, right? And I was very descriptive here. Events that are not independent. In other words, where it does affect the probability of the other one. In that last example, would you suggest that the choosing of the queen, knowing that the king has already been chosen, and not putting the king back in, would that be independent or dependent? Okay, dependent, because did the probability of getting the queen get affected? It did. So how could we make that independent? By simply putting the king back in, exactly. So one way to check this, independent events. For example, in that last one, it would have been independent had that just equaled that, correct? Right? They would have been independent if the king really didn't affect the probability at all, correct? So if they are dependent, what happens is, in this case, this is what happened to us, correct? Would you agree that's what happened to us in that first problem? Probability of Q given K was not the same as just the probability of Q just by itself, correct? So that made them dependent, okay? They are independent if actually these two end up being equal, okay? Which is logical, right? So to decide whether the events are independent or dependent, selecting a king from a standard deck without replacement and then selecting a queen. Well, we just talked about that one. Which one is it? Dependent? Are you sure? Okay, I was just checking. Tossing a coin and getting a head followed by a tail. Well, you probably want some clarification. Yes, it's the same coin. Very good. It's a little unclear, don't you think, based on what you have here? Tossing a coin, getting a head. Picking up that coin, tossing it in, and getting a tail. Does the probability of getting that tail get affected by you getting a head on the first one? No, it does not, does it? So this is, then what? Independent. Would it? No. Okay. The question was, would it matter if it was a different coin? No, not really. Okay. But I want you to start looking at these problems a little bit without making assumptions. Okay. Selecting a jack from a deck. Replacing it. I thought there was a typo there for a second. And selecting another jack. Does that first jack that you picked affect the second one in this case? I've heard both. I replaced it, correct? So does it affect the picking of the next one? No. Does not. So then what is it? Independent. Question so far? Okay. This is going to be big, and this is actually something we're going to manipulate a lot when we come back to this later in the year. The probability of two events A and B will occur in sequence, meaning in that order, is probability of A and B, so is equal to the probability of A times the probability of B given A. If the events are independent, I can basically just take off that whole given A part at the end. Why, if they're independent, can I just take that off? Because is knowing that A happened really going to affect B if they're independent? So do I have to worry about that stuff at the end? Not really, okay? And so it's very helpful to notice if they are independent or not, because then it's a little bit less work. Again, when we really get into notation later this year, you're really going to want to know that, okay? Because we're going to get much more general. Okay? So let's try a few and see if we can figure this out. Selecting a king, followed by a queen from a standard deck of cards without replacement. Now, is this the exact same as the first question I asked you? Is it very close to the first question? Now I'm not saying this anymore. Probability of a queen given king, right? That's not what I'm saying anymore, is it? I'm not saying that. I'm now saying probability of, I'm now saying that. I'm getting both of them, correct? I'm not picking one and not caring what it is, or putting it back, not putting it back. So here I am picking a king. I'm leaving it out, and then I'm going to pick a queen out of there. Okay, again, without replacement. So according to our rules, should I write it the other way? I don't know. I think this way's fine. Yeah, this way would be fine. I got to find the probability of getting a king. I think it times the probability of getting a queen, knowing that a king has just happened, correct? That's really what I'm trying to find. So how about the probability of getting a king? That's probably the easiest, right? How many are in that sample space? How many cards are possible there? 52, correct? So out of that 52, how many are the outcome I'm looking for? Right, so 4. Now, a lot of times I don't simplify these because later on this year, you're not going to want to simplify them. So I just leave them for now. And who knows what's going to cancel anyways, right? Some other stuff might cancel even better. So how about the probability of getting a queen knowing that the king has already happened? Well, that actually is the first problem we did, isn't it? Right there. And what did we find out earlier? That was 4 out of 51. Okay. So now do you believe it's worth possibly simplifying the first one? It probably is, right? But a little bit later on, we are going to have some addition, and we might want to keep it. Okay. So this is just, what, 1 out of 13, right? So in other words, 1 times 4 is 4. Anybody got 13 times 51 figured out yet? What is it? 663? Yep. So is that very likely? No. And that's flat out saying you pick out a king, and then you go right back in and you pick out a queen. Okay. So now if we tried it 663 times, are we guaranteed it would happen 4 times? Would it probably happen 4 times? It's probably not even all that probable, is it? Okay. Could it happen 10 times? Is that something that's possible? Could it not happen at all? Yeah, all of those things are possible, right? We got to watch out possible versus probable. Okay. How about tossing a coin and getting 3 heads in a row? Oh yeah, 3 tails. Well, it's the same probability, right? So I tossed the first coin, and what's the possibility of getting a tail? 1 out of 2, right? Does that first coin affect the second coin? No. So what is the probability on that one? How about this next one? 1 out of 2. So that's basically this taken out like 3 times is what it is. It's probability of tail 1 and tail 2 and tail 3. But that and really turned into what? Multiplication, correct? So in other words, it is. So in other words, if I ran that trial 8 times and I tried that tossing it 3 times, they're saying it would probably happen once that I would get 3 tails in a row. Again, could we simulate that? Yeah, we could actually do that one, right? Okay. And if you want to, you can try some other time. But you have to know what the trial is. The trial here is flipping it 3 times and getting 3 heads, or 3 tails, right? How about selecting a king, replacing it, and selecting a jack? So it's basically probability of that, correct? So it really is still that, but we have to really watch out on that one. How about the probability of a king? That really hasn't changed much, right? That's 4 out of. How about the probability of getting the jack knowing the king has already happened? Well, we have to know exactly what happened with the king. It got put back in, right? So it's basically same thing, right? Because that card's back in there, so I once again have 52 cards in that sample space, and now I'm trying to get a jack. Well, there's 4 of those, right? So in other words, it's 1 out of 13, right? And 1 out of 13. So in other words, 1 out of. Yes, we have a question. Ah, very good. Someone said in that last one, could I have written probability of king times probability of jack? I could have, because look back at your rule. if I know they're independent, do I have to worry about that whole given this thing? No. And should we have known in this last one that they were independent of each other? Yeah, so we could have just jumped and just done that, exactly. That's why that works, right? Because it doesn't affect it. All right. A coin is tossed and a die is rolled. Oh, sorry, a number cube. Calculate the probability of getting a head, not like a head of someone, but getting a head flipped, and then rolling a 2. Can we do the independent formula here? Are these two independent of each other? Yeah, it's a coin and a die. You know, there's nothing really going to happen there. Yes, number cube, sorry. So we're looking for the probability of head and 2. So in other words, you're saying I can just do, yeah, you got to fill it out though. That because they are independent, and you are correct. I don't have to worry of 2 given the head has been flipped. So probability is, for the first one, 1 out of 2 because there's only 2 possibilities in the sample space, and I only want one of them is the outcome I'm looking for. And how about this one? Yeah, there's 6 possible in the sample space, and only one of them that is what I want to have happen. And so 1 out of 12. Okay, these next 3 can get rather interesting. The probability that a salmon swims successfully through a dam is 0.85. Yeah, salmon. Yeah. Calculate the probability that 3 salmon swim successfully through the dam. So this is one of those lower ones, kind of like maybe the one we have here where they could possibly jump up to go upstream, right? So probability, basically, salmon 1 and salmon 2 and salmon 3 make it through, correctly? How about the probability of salmon 1 making it through? 0.85. Now that I know that one salmon has gone through, does that affect the probability of the next one? No, it basically says here, right here, it tells me the probability for every individual salmon is 0.85, right? And pretty much no matter what has happened before that. So these are independent events. So I can just go ahead and have another 0.85. And the third one is also 0.85, and that says and, right? It's salmon 1 and salmon 2 and salmon 3. So that and turns into multiplication. So in other words, 0.85 to the third power, right? Which is 0.61. Well, we'll just go to 0.61. You say 4-1 or 1-4? 1-4? Okay. So in other words, 3 of them would be 61.4% chance that 3 of them would get through. Okay. Yeah, not really good for the species, is it? If you think about it. Yeah, that's not so good. All right. So now, same scenario. Calculate the probability that none of the 3 will get through. How could we do that? Yeah. Exactly. Now, here's where a lot of people do that one wrong, and I'm going to talk about it in a second. What we have to do is basically say, well, we know the probability of success is 0.85 in each event, right? So the probability of failing in each event is 0.15, correct? Or 15%. So we would take salmon 1 is a no-go. Salmon 2 is a no-go. Salmon 3 is a no-go. Well, we don't know that they died. They just didn't make it up through the dam. All right? So 0.15, the third power. It's not very big. 0.00. So 3, we'll say? Huh. Doesn't that seem suspicious? Shouldn't these 2 add up to 100%? Why not? Okay, there's 3 different salmon. Okay, good. But why don't they add up to 100? This one is saying they all make it. That one's saying none of them make it of the 3. Yeah, isn't there other options? Like, isn't it 2 make it and 1 don't? 1 make it, 2. See, there's other options, correct? So the probabilities do get spread to all of the possibilities, right? Okay. And then once I add all the possibilities up, it's 100. But do you see how some people could think that this total should be 100? That's why here's what some people tell me how to solve C. They say take that answer and subtract it from 100%. Okay? Because we're thinking of that complement idea, correct? But you have to make sure that it's all other options. Is this one down here all other options beside the one that's up there? It is not, is it? There's lots of in-betweens, as you called it, right? But did we really use the complement idea in this problem? We did. These two individual ones are complements, right? This is 0.85 made it, 0.15 didn't make it, but they were individual for each individual salmon, okay? So let's try this one. Calculate the probability that at least one of the salmon is successful in swimming through the dam. Yes? Okay, I've been told that it should be 0.85 times what? Times? Well, I have a problem with that, though. This is what I was told. You're basically saying that it has to be the first one. Oh, wait. Subtract 0.003 from what? Okay, so let's talk about this. At least one gets through. So that means one gets through, two gets through, or three get through, correct? So in other words, the only one that's not considered there is that none of them get through, correct? So is this answer up here actually the complement to D? That actually is the complement. Is B the complement of C? No. But D is. Okay, so this isn't going to quite work because we can jumble up which fish got through, right? So at least one got through. It'd be easiest just to do 1 minus that. And let's face it, at least one of them getting through, if just of the three, if 85% for just one getting through, this should be a pretty high percentage, right? If all I want is at least one of them, because it's 1, 2, or 3 get through, should be relatively high. Okay. Okay, are you clear? I'd say the last three here are probably a lot of times the one that caused the most trouble. Are you okay? The complement can save you a lot of work, because actually doing this problem more along the lines of this way takes a very long time. You have to write out all possibilities. Right? That would take forever, right? But then we have to add them up. So that's not going to work, okay? You can, but it's a lot quicker just to use the complement. Anything else? But knowing when to use the complement and how to use it is very important.